Linear regression. Linear regression is one of the simplest yet most fundamental algorithms in machine learning. First developed in the early 1900s by mathematicians like Carl Friedrich Gauss. It works by finding the best straight line, a set of data points, making it perfect for predicting continuous values like house prices, stock prices, or sale forecasts. What makes linear regression stand out is its simplicity and interpretability. You can easily understand exactly how each input affects the output, making it ideal for beginners learning machine learning concepts. However, linear regression has significant limitations as well. It assumes that the relationship between variables is always linear, which isn't true for the most real-world problems. It's also very sensitive to outliers, meaning a few extreme data points can completely throw off your predictions. Additionally, it struggles with complex patterns and can't handle categorical data without preprocessing, which is why more advanced algorithms often outperform it in practical applications. Decision trees. Decision trees were popularized in the 1980s and work exactly like their name suggests. They make decisions by asking a series of yes or no questions, creating a tree-like structure of if-then rules. For example, when predicting if someone will buy a product, it might first ask, is their income above $50,000? Then, are they under 35 years old? And so on until it reaches a final prediction. This makes decision trees incredibly easy to understand and explain, even to non-technical people. The biggest advantage of decision trees is their interpretability. You can literally trace the path of decisions to see why the algorithm made a specific prediction. They also handle both numerical and categorical data naturally and don't require much data preprocessing. But decision trees have serious downsides too. They're prone to overfitting, meaning they memorize the data so well that they fill on new, unseen data. They are also unstable. Small changes in the data can create completely different trees, making them unreliable for consistent predictions. Random forest. Random forest, developed by Leo Breiman in 2001, solves many of decision trees' problems by combining hundreds of thousands of decision trees together. Instead of relying on just one tree's opinion, it takes democratic vote from all trees to make the final prediction. Each tree is trained on a different random subset of the data and considers only a random subset of futures, which prevents overfitting and makes the algorithm much more robust. Random forest is incredibly powerful and versatile. It works well for both classification and regression problems, handles missing values automatically, and provides future importance rankings to show which variable matter most. It's also relatively fast and doesn't require extensive parameter tuning. However, random forest loses the interoperability that makes single decision trees so appealing. With hundreds of trees voting, it's nearly impossible to understand why a specific prediction was made. Turn it into a black box algorithm. Support vector machines. Support vector machines, or SVM, were developed by Vladimir Vaknek in the 1990s and work by finding the optimal boundary that separates different classes of data. Imagine trying to draw a line that best separates cats from dogs in a dataset. SVM finds the line that minimizes the distance to the nearest data points from both classes, creating the most robust separation possible. It can also use kernel tricks to handle nonlinear relationships by transforming data into higher dimensions. SVM excel at handling high-dimensional data and works well even with limited training samples, making it popular for text classification, image recognition, and bioinformatics. It's also memory efficient since it only uses a subset of training points called support vectors. But SVM has also notable weaknesses. It's computationally expensive on large datasets, doesn't provide probability estimates naturally, and choosing the right kernel and parameters required expertise and experimentation. K-means clustering. K-means is an unsupervised learning algorithm developed in the 1950s that groups similar data points together without needing labeled examples. It works by randomly placing cluster centers, then iteratively moving these centers to minimize the distance to surrounding points until the clusters stabilize. You need to specify how many clusters you want beforehand, which can both be a feature and a limitation depending on your use case. The beauty of K-means lies in its simplicity and speed. It's computationally efficient even on large-scale datasets and easy to implement and understand. It's widely used for customer segmentation, image compression, and market research. However, K-means assumes clusters are spherical and similar in size, which often isn't true in real data. It's also sensitive to initialization and outliers, and choosing the right number of clusters can be challenging without domain knowledge. Neural networks. Neural networks, inspired by biological brain neurons, were first proposed in the 1940s, but gained popularity in the 1980s with backpropagation. They consist of interconnected nodes organized in layers, where each connection has a weight that gets adjusted during training. Information flows forwards through the network, and errors are propagated backward to update the weights, allowing the network to learn complex patterns and relationships in data. Neural networks are incredibly versatile and can theoretically approximate any continuous function, making them suitable for everything from image recognition to natural language processing (NLP). They can automatically learn features from raw data without manual feature engineering, which is why they've revolutionized fields like computer vision and speech recognition. But natural networks require massive amounts of data and computational power to train effectively. They are also complete black boxes. It's nearly impossible to understand how they make decisions, which can be problematic in critical applications like healthcare or finance. They are also prone to overfitting and require careful regularization and validation. Gradient boosting. Gradient boosting, popularized by algorithms like XGBoost and LightGBM, builds models sequentially where each new model corrects the mistakes of the previous ones, like random forest, which builds trees independently. Gradient boosting creates a chain of weak learners that gradually improve the overall prediction accuracy. It's like having a team where each member learns from the mistake of those who became before them. Gradient boosting often achieves the state-of-the-art performance in machine learning competitions and real-world applications, particularly with tabular data. It handles missing values well and provides feature importance insights. However, it's computationally intensive, requires careful hyperparameter tuning to avoid overfitting, and can be sensitive to noisy data and outliers, making it more complex to use effectively than similar algorithms. Watch this video to discover the best free tools and softwares that every game developer must have.